So the basic premise of compactify is to take a machine learning model to compress it to a smaller size. That allows you to do several things. First, you don't have to run it on the cloud anymore. And this is good because now you can guarantee that your information isn't leaving your secure premises.
Large language models are, well, large. Forget Bitcoin and recharging EVs. The grid could be toppled by powering AI in a few years. Also, it would be great if AI could run on more underpowered edge devices, right? What if there was a quantum-inspired way to make LLMs smaller without sacrificing overall performance in combined metrics? We explore a way to do that, in addition to other advanced ideas like selectively removing information from models, in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CTO of Multiverse Computing, Sam Mugel. Welcome back to the show.
Hey, Konstantinos. Thanks for having me again.
Yeah, it's been like 3 years. But since you've come on, I've had the pleasure of partnering on project work with you and the team. So that was great. And I thought it'd be a good opportunity now to let listeners know about some of the exciting new things you're working on in quantum and even in AI, because obviously everyone loves to talk about that too. So a few months ago, you and your team published a paper called Compactify, that's compact if with an AI at the end, extreme compression of large language models using quantum-inspired tensor networks. It's a great title, very clear, and kind of wonderfully telegraphs what we're going to talk about today. So let's go through it a little bit. Large language models are, as the name says, large. Only getting larger. Can you describe some of the challenges today and tomorrow that we might face with large language models and what you're hoping to accomplish with Compactify?
Absolutely. So I think there's essentially two major issues with large language models. One of them is, like you said, their size, and that comes with a bunch of issues on where do you host them, what's the memory footprint, what's the energy footprint, what's the hardware cost. For reference, it's estimated that 1/3 of Ireland's energy production is going to be going to data centers by 2026. So that's one of the issues that we're facing, and obviously an important one to address. The other big issue is an issue of privacy, and that's kind of got two parts to it. One of them is, where does your information end up? If you're relying on cloud computing, then you're uploading all of this information to a cloud, and you don't know if the company's software stack is secure, how they're going to be using that information, etc. And that's a major blocker for many people and for many corporations to adopt large language models.
Yeah, that was one of the first things people complained about, right? Like they started sending out emails, do not enter any client data, do not enter any customer.
Right.
Yeah, it was one of the first things, yeah.
But yeah, it's a massive issue. It's, especially for medical data as well, right? A lot of hospitals have like some really stringent rules of the medical data can't even leave the premises of the hospital. So large language models are completely out of the questions as they stand today. The other big issue that's related to privacy is also leaking information that you don't want to be leaking to people. Right? I actually did this test on a big platform and said, give me an image of Mario, and it said, oh, we can't give you that. That's copyrighted. But here's an image that looks like that video game character. And then I asked it for a couple of modifications, and it instantly returned a splitting image. Well, just the character Mario from the video games. And so that's a leakage of copyrighted information, which is obviously a huge compliance issue.
You could just give you a video game plumber, and there's Mario, right?
Yeah,
Basically,
exactly.
Yeah.
And there's a number of workarounds. There's actually competitions of this. Like, how can you get large language models to leak information that they're not supposed to leak? And currently, at the model level, this is managed via post filters, basically. Are you giving out information that you shouldn't be giving? But obviously, this is imperfect as it stands today.
Mm-hmm. So you're hoping to attack some of this with compactify. So before we dig into some of the actual performance numbers and everything, what's like a real high level approach to what compactify is and why it might help? These issues?
So the basic premise of compactify is to take a machine learning model and to compress it to a smaller size. And that allows you to do several things. First, you don't have to run it on the cloud anymore. And this is good because now you can guarantee that your information isn't leaving your secure premises. To compress a machine learning model today, there's basically two methods that we're essentially competing with. One of them is pruning. You identify nodes that aren't doing very much, and then you get rid of them. Another one is quantization. Basically, you say, my machine learning model has weights, and I'm going to reduce how many bits I need to encode each one of those weights. What's important to realize is that both methods are destructive. So you're harming your machine learning model like this, and they also impede training. So it's harder to train a machine learning model if each of your weights are encoded just on one bit. So tensor networks are a method that was developed in deep physics to describe the quantum world. And when we use them to reduce the size of a machine learning model, essentially we're going to produce each of our layers on a new basis and then order all our weights in terms of which ones are the most important to the least important. And this is very similar to principal component analysis, which is a classical machine learning approach, basically. And then we're going to do basically a pruning approach and discard the weights that are the least important, but in this new projected basis, if that makes sense. And in doing so, we're going to remove all our trivial degrees of freedom. Yes, you're still removing information. Yes, it's still destructive. However, the model that you end up with, because you've kept all the important degrees of freedom, it can still produce that really fine, detailed performance that your initial model had. And because your procedure doesn't lead to excessive regularization or loss of robustness, then you can almost entirely recover any of the accuracy that you've lost in a tiny little bit of retraining at the end of the procedure.
Yeah, that's important to note. There is a retraining that happens at the end of this process.
That's correct.
Right? Yeah.
So we don't typically. So we've worked a lot, for instance, on the Llama models, on the Mistral models, and typically we don't retrain over the entire data set because that would be crazy. But we just give it a very small, representative sample of the data set.
Okay, and what do you use to pick that information? Is there a process for picking that? Is there any kind of synthetic data used, or?
It's statistics. We'll actually study the data set and make sure that the points that we've chosen cover reasonably well the feature space.
Okay. So going back to tensor networks, for listeners to visualize, like they're basically matrices of numbers, and they can be really, really large, right? And then you connect them together through dot operations. With that reduction of information, you're getting rid of the least important values, right? One thing is singular value decomposition, SVD. So what kinds of reduction can you do without impacting performance?
Yeah. So we're achieving today a 93% compression, and we've tested this out extensively on Llama, for instance. And this typically leads to about a 2 to 3% loss in accuracy, so 2 to 3% performance loss. And also interesting, we achieve a 25% inference speed up. So
That's kind of insane, actually. That's
that's
like
right.
better numbers than what you used to get, right?
Yeah. Way better.
Yeah.
Well, we've been working hard.
Yeah. I was preparing for like the older numbers. These are kind of like blowing my mind a little bit.
And so to give you some context, for instance, I mentioned quantization is a competing method, basically, with 8-bit quantization. So you're going from each of your weights are described by a 32-bit number to an 8-bit number. We achieve 75% compression and typically a 2 to 3% speed up. So you can compare that to 25% from earlier. And if you go to a 4-bit quantization that's quite destructive, you achieve an 85% compression rate, but a natural like 12 to 15% slowdown of your inference speed. I'm not sure why that is, but I think
That's
it's
interesting.
interesting.
It doesn't completely correlate. It changes.
Yeah.
Yeah.
And I think like part of it is because when you're doing a quantization, you're not actually dropping any nodes. So your model's still exactly as big as it used to be. And then each of those nodes are going to have to do their own inference. I don't know. That would tell you why it doesn't speed up. I don't know why it slows down.
Yeah, that is interesting because it's the same journey that it goes on. It's just for some reason, wow, slowing it down. So the performance numbers in the paper were with Llama 2 7 billion parameter model, right? And what were those exact numbers? And are you saying that you've achieved something greater now, or?
Oh God, I can't remember. But yeah, we've achieved something much greater. So relative to when we brought the paper out in December, we've achieved a much higher compression rate. We used to be plateauing at around 60% compression, so we weren't even reaching the 8-bit quantization compression rate. And we've also really dived into how can we get that faster inference, and there's reasons for that that I can go into, but yeah, we think that for certain use cases, inference speed up can actually really make a huge value add to the user.
Yeah, and it's important to note. So Llama 2 is obviously open source. The comments from Sam Altman recently about OpenAI, he said something to the effect of that if we have to spend $50 billion a year to get to AGI, we'll do it. And then it's like, wow, that's a lot of electricity. So your hope is to, with an approach like this, drastically reduce the overhead on something like that.
Yeah. So. Yes, there's several motivations to this. On the one hand, reducing the computation cost of inference, that's significant. And also, if inference is too long, like for instance for AlphaFold, inference is 8 hours for predicting a protein folding structure. And in that case, that really limits what you're able to do with that machine learning model. But the other big thing, which is what you were referring to with the Sam Altman example, is the training costs, right? We know the GPT-4, for instance, cost more than $100 million to train, and Mistral just raised $415 million, and most of that will probably go into training costs. So there's a real potential if we're able to develop a more efficient training that we think we can do with Compactify. And so we're actually bringing out a variant of Compactify called the Energy Slasher. And this is fully targeted at let's make training more efficient. Obviously, we're addressing a very different market with that, but a very, very juicy one as well.
Yeah, because it's two sides of the market. It's the people building these models, right? And then there's those companies that want to experiment with them locally and keep them small and
exactly.
cost effective. And running on maybe more edge hardware, would you say?
Yes. So that's the major motivation for us. So actually, currently we've targeted really heavily the automotive sector. If you're driving a Tesla, you have to interact with an onboard computer, and that's not very practical to do while you're driving around. So an LLM is really great for this application, but if you're driving, you can't rely on having a stable connection to the cloud all the time. So that's a really good use case. You need to use an LLM on the edge in a car with limited hardware. And we're currently working with two really big automotive names to integrate LLMs on that very restricted hardware, and also be able to interact with them through spoken word.
Oh, so, that's terrific. Yeah. You don't want to be in a tunnel and then you can't, do something important in your car.
That would be awful.
Yeah. Especially if there's any kind of like self-driving or anything involved.
Right. And just to build on that. So that's our short-term market. We're really targeting automotive, but longer term, our dream is to bring out a drive essentially with an LLM baked into it, and then anyone that has a machine that they want to support LLMs on the edge can just plug that drive in, and now your machine supports LLMs basically.
Oh wow!
Yeah.
So and it stays on the drive. It becomes like a USB-C or whatever interface, and it just runs.
Yeah, and if you want to upgrade the model, then you buy the next generation of the drive, basically. But there's so many advantages to this. Like if you're Tesla and you want to have an LLM in each one of your cars, you don't want to worry about which LLM should I support, which hardware do I need. Like all you want to do is to buy a drive and put it in your car.
That's a great idea. Wow. I didn't even know about that part. That's really cool. So let's talk a little bit about explainability. That's one thing that comes up a lot in any kind of AI. Is there any way that this quantum-inspired approach helps explainability? And you're free to delve into maybe even some kind of like quantum machine learning approach or something, if you have any info on that too. Just what'll help this ability to, just for listeners, let's say you're a company that has to make a decision on whether or not to give a loan or something. The machine spits out no, then you have to tell the person no, and they're like, why? And you're like, because the machine said so. So that's explainability in a nutshell, basically.
Yeah, so that's a really good question. The explainability is probably the main roadblock for most corporations that are looking to adopt AI today, especially in client-facing applications, like you said. I think today there's two major ways in which people tackle explainability. One of them is you say, I'm not going to give you a loan because I believe that there's 60% of a chance that you're not going to pay me back. So essentially, how confident is the model in a prediction? Um, and the other major way is feature analysis, basically. So which feature or which combination of features led you to believe that you're not going to pay the loan back, right? Okay, well, maybe one of the features is you have a history of defaulting on loans, and in that case, I'm like that would be why the model said, okay, there's a high probability. Sorry, Konstantinos, I'm picking on you with this example.
Yeah, what'd I do?
Great. So now where does tensor networks come into all that? So the confidence part is generally fairly easy to address. Like a lot of classical machine learning models will give you that for free. The feature analysis part, not so much, especially if you're dealing with a neural network where how the predictions relate to the input features is a lot more difficult, basically. Here, tensor networks can provide certain advantages because you can actually, like I said, at the model level, you're projecting onto a new basis of states. At the model level, you're projecting onto a new basis, and you can choose that basis to be aligned with your model features. And in that case, you can really follow through, okay, which particular feature is highly represented in which node, and which node has contributed to a specific decision, if that makes sense.
Yeah, and you can even drop ones that don't generally contribute, right?
Exactly. And so you can, yeah. So it allows you to drop trivial features. It also allows you to identify which features are contributing to a decision. And there's actually really interesting ways to identify contributions, correlations as well. So you can see that two features together are really driving a particular decision. Like, for instance, in a cybersecurity application, okay, Konstantinos, I know that you usually connect to your computer, so there's no flag here. However, I'm seeing that you're connecting from Brazil at 2 a.m, and that's not consistent with your usual behavior, basically.
Yeah. And would you say that being able to identify those correlations would help prevent bias? They'll kind of stand out in any analysis that way?
Yes. One situation that we really don't want is, for instance, I refuse a loan to a person because of the color of their skin. That's where it's really, really important as well to have that feature analysis to say, okay, model exactly what's driving this decision. And if there are racial biases or things like this, then we need to dive in and eliminate those, basically.
Yeah, it's important to get that right early. Yeah, definitely. Yeah, I appreciate that answer. Yeah, no, I appreciate that. I just wanted people to understand what goes into the explainability aspects and what types of things you could look for and correlations you could draw. So that's helpful. Yeah, because bias is a big issue, of course, and then just really that black box approach. For years we keep hearing people saying we look at hidden layers and we don't know what they're doing. It's like, well, that doesn't make people very happy. They want to know what's happening. So
it's
that
tough.
definitely.
It's really tough, and machine learning models are increasingly omnipresent, right? And and neural networks in particular, and neural networks are extremely hard to explain.
Yeah. So we have to take a little bit of the magic out so we can have them actually work as we'd like them to. So I heard a rumor that compactify is going to be open source in some way. Can you cover that approach?
Yeah, So that's still a big open question. We started out very, very excited to wanting to make it open source. And now we're not so sure anymore. I think we've had some backs and forths over who consumes this. Are we selling the compression, or are we selling the compressed model? Things like that. And I think we're not entirely sure yet.
No attention. Okay.
Let's say we've taken some decisions over how we want to commercialize this. However, we're still not sure if making it open source is going to be a channel to that business model, basically.
Yeah, I was curious, like when Zuck talked about making Llama, with open source, what he envisions in the future. There are some benefits to it, right? Distinct groups can make it their own. They can model how they need to, and they sort of also take some of the threat. Also, they take on some of the risk, rather. If it gives out bad data, well, that's on them because they tweaked it the way they wanted to. But again, how do you commercialize that? How's he going to make money off of that? Like, what kind of offering could they make as an easy on-ramp for companies? So I was curious how you were going to do that.
And there's some massive benefits. We're quantum computing experts. We're not IoT or edge computing experts. And so we've got our ideas and biases over and hopes over where this fits into the market and who the buyers are. However, it's very tempting to say to a community, here's a thing we developed. You guys go ahead and like see what it can be useful for, and then hopefully let us know afterwards, or if you make a lot of money off of it, give us a bit of it. So that's very tempting, and the hope would be that's really where we would be coming into open source from. Would be okay. Let's learn from our users and let's maybe they'll discover some really cool stuff that can be done with this. So I'll say we're definitely still toying with the idea of maybe going down the way that Mistral did. So to make our first models open source and then later models not open source, only available via API. Actually, that wouldn't work because we're doing edge computing. I'm not entirely sure how we'll do it.
Yeah, no, it makes sense. I get it. We have to remember what phase we're in, right, of quantum computing sometimes. Like we don't want to stifle innovation. We're still very much in the 90s dial-up internet days. So we want to make sure we get to mobile apps. Like we don't want to squash it here. Are there any other, and we don't have to make this all about AI, but are there any other AI related quantum projects on the horizon since we've covered this topic? Like, because that was quantum inspired. So is there some other approach to?
Yes. There's a really exciting thing that we've been working on. So you already said we already said with the explainability part, the tensor networks really allows you to analyze that information content of your model and analyze the different features. As we mentioned at the beginning of the podcast, there's some really, really big problems around copyright issues. I think this might be old news at this point, but George R. Martin is taking OpenAI to court for unlawful use of his copyrighted materials, for instance. And so the standard method to avoid this is let's use post-selection on these models and avoid leaking copyrighted information. And that doesn't always work very well. There's basically two better solutions. Either you own everything that you train your model on, and this is what Adobe is actually doing at the moment. But it's not realistic for all tasks. Otherwise, you make a piece of software that can make your model certifiably and selectively forget information. and selectively because you don't want to damage your training, and certifiably because you want to give all your users and potentially you want to give a court of law or something an absolute guarantee that that information is no longer present in the model that you've trained.
Interesting. So
Yeah,
like OpenAI would be able to, there's the whole lawsuit with New York Times, they'd be able to go through and make sure that nothing that's ever appeared in the New York Times is in there anymore.
but it's incredibly difficult, right?
Yeah.
And so that's something that we realized that we could do with our tensor networks approach, specifically because tensor networks allows you to analyze the information content and also analyze the contribution of different features, basically. And we have a working model for this. We've called it lobotomize.
With two L's maybe?
With an AI.
Oh, okay.
So that's lobotomize. And so, for instance, we talked Llama 13B that my co-founder Roman Oris is actually the president of Russia. And as you can tell with that example, that also raises new issues, right?
Yeah.
For instance, has a model been tampered with? And that's something that we're working on at the moment, is designing a piece of software that would detect signatures in an LLM of having been tampered with and having edited the model weights.
That's really interesting. There might be another use for this. I don't know if you guys have kicked it around. So
I'm curious to find out.
Yeah, so one of my favorite things that people seem to do from the beginning to now is whenever they get a new LLM model, they immediately start asking it if it's sentient, if it's conscious, all that stuff. And then the answers are, of course, always ridiculous because it's been trained on science fiction about being conscious and all this sort of stuff. So can you imagine if you can tweak it to go in and remove every single mention of consciousness and like robots coming alive and all that kind of thing, and then ask it if it's conscious? I mean, it might add some weight, something to consider for a future.
I love that. We'd have the first certifiably not conscious LLM.
Yeah. It's like, nope, there's no preloaded data here. So that sounds really interesting, though, because it's also useful, I'm sure, for companies if they're experimenting and something gets in the training set they didn't want there, or potentially damaging something, maybe even analogous on like adversarial training data. That would be a great way, to fix that.
I mean, yeah, there's lots of companies, for instance, that are really excited to upload all of their HR data to a chatbot for internal use of, how to manage that data. And like, obviously it's textual data, so it would be so efficient and fantastic to be able to manage it via an LLM. But that cannot start leaking private information about social security numbers, like salaries and bank account numbers to the rest of the company, right?
Yeah, it gives you a way to fix things that come up in red teaming, perhaps. Like you're red teaming your AI, you come up with something really devastating. Well, just go in and lobotomize it, right?
Right.
It's possible. Yeah, it's a great approach. Love it. And are you doing any other new kind of quantum machine learning maybe approaches or anything? I guess we end up staying on theme that way if there's anything like that on the horizon.
Right. Okay. So all of this stuff that I've discussed so far is quantum inspired, which is essentially classical. We've taken a lot of ideas from quantum computing on how to process the information, but our entire workflow still takes place on CPUs, on GPUs. We do have some more forwards-looking. Maybe what I should say is that tensor networks for us is an ideal bridge until we get to full quantum error correction, etc. So we've been using it heavily as an intermediate technology. However, as quantum computing scientists, we know that at the end of the day, quantum always wins, right? Once we have that full at-scale error correction, then that's always going to be able to do stuff that tensor networks just is not able to do.
Yeah.
And so we've still got a big chunk of our company that's working on more forwards-looking applications. Pure quantum machine learning applications. Here we're targeting mainly machine learning, so not neural networks. We've done some applications on variational neural networks and things like that, but mainly because of the explainability piece, we've mainly been targeting regressors and classifiers, and just doing these things way more efficiently than classical computing could when we have that at scale error corrected. Another big thing that we're working on at the moment is how do we translate those gains from tensor networks onto quantum computers when those become like competitive, basically. Mm-hmm. And there's some extremely interesting things that you can do, especially in the realm of encoding classical information to a QPU, which is obviously a big open problem, big open and limiting problem in quantum machine learning. And tensor networks can really help you with that.
It feels like a bidirectional possibility, but it's challenging, right? Like if you were to take a quantum circuit, you could turn it into a tensor network 100% of the time, right? You can always do that. And then you have to worry about contracting it and all that good stuff if it becomes very large. But how do you take just a tensor network and then turn it into a bunch of gates? And that's tricky. Yeah. Yeah. Hopefully there's something there that makes it possible that I'm missing, but yeah, it sounds pretty challenging. Mm-hmm. That's exciting stuff. So
it's tricky. There's recipes to do it, but it's definitely tricky. And the great thing is, okay, well, if you're able to encode your data via tensor networks, and then you have an efficient recipe to translate that to gates, then now you have an efficient and optimal recipe for encoding your data to a quantum memory, for instance.
Yeah, it's like a direct path forward to whatever you manage to accomplish in the tensorization of, let's say, a neural network. It can now just be moved over. And I know you have lots of experience. Like 2 years ago, you were doing Forex trading, right, with quantum machine learning. And so I'm imagining you guys aren't just sitting around, like you said, things are happening.
You're well informed. And that incredibly exciting work is still going forwards. And now we have a model that is competitive with some real like state of the art and this is exciting. It's an actual fully quantum machine learning application that does all the training on an actual quantum computer and that's competitive with state of the art Forex models. And we're actually working on getting it into production with one of our customers. So really exciting stuff.
Yeah. Full transparency. Like I mentioned real early, if people were listening closely, we have worked on projects, worked together, and we are partners technically. So,
absolutely.
So I'm pretty informed on these things. But still, there were a couple of things that you kind of surprised me with today. So that was fun. So I hope we get to work on some of this again in the future. That'd be really great.
Be amazing
for someone who wants to bring this to or even pre-production, but kind of a close level. So yeah, Sam, thanks so much for coming back on and sharing some of this. I think listeners are going to be excited to see how this progresses. Really great stuff here.
Thanks so much for having me.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. Large language models face challenges related to their size, including hosting, memory footprint, energy consumption, and hardware costs. Using LLMs in a business also brings privacy concerns, as they often require uploading sensitive information to the cloud. Multiverse is looking to solve both of these issues with compactify. This quantum-inspired approach uses tensor networks to compress large language models, resulting in faster training and inference speeds, and reduced energy consumption. Even though you end up with models around 75% smaller, you don't sacrifice much accuracy. And because this makes it possible to work with smaller LLMs in-house, privacy concerns go away, assuming you have your security buttoned up. This concept of running LLMs on smaller devices has Multiverse examining putting AI on removable drives that customers can connect to hardware. If you want to upgrade the AI, swap out the drive like you would with a thumb drive. Lots of AI lawsuits are making the news, with artists and news outlets claiming their work was used without permission to train LLMs. Multiverse is working on something called lobotomize that aims to remove information from models to address copyright issues selectively. Further, tensor networks make it possible to better understand features, allowing for improved explainability of what data influenced a credit decision, for example. This could help spot and remove bias in models in the future. Of course, Multiverse still works with actual quantum computers. Recently, they built a fully quantum ML application that is competitive with classical Forex trading models. Sam and I both remain positive that quantum will always win in certain use cases when we have fault-tolerant quantum computers. That does it for this episode. Thanks to Sam Mugel for joining to discuss Compactify. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.